Meet the unit circle. This is something we're going to use for quite a while. Very important that you have a nice clear copy of this diagram and that we can discuss it and that you know these connections well. So we're going to get going on this by starting with what the unit circle is. It's just a circle with radius 1. Now you kind of met the unit circle when we talked about radians because that's where radian measure comes from. It's the arc length around a circle of radius 1. Right? So instead of saying that we're dealing with 360 degrees, we're dealing with 2 pi with radians because 2 pi is the distance around a unit circle. So on this diagram I've got here, we're trying to connect this circle to trigonometry. That's why there's a triangle in the middle of it like that. So this would be like the angles that we were dealing with in standard position, right? And now I've shown you how to get a triangle. Does anybody remember what that little red angle's called that I put in there? Reference, yeah, reference angle. So remember, the most important one we deal with is the reference angle. Out of all the stuff that we talked about in standard position, most of it is just to help prepare you to know what a reference angle is. Okay, so super important that we know the reference angle. And we also know that this length of the triangle is 1 because it's a unit circle, radius 1. Now, if I'm on a point and I'm at, say this point here, we call that point x and y, right? We give it x coordinate, y coordinate. So in this triangle, what I can do is I can label this is x and this is y, and that brings me to the point xy. So this is the setup, and now I'm going to make the connections to trig for you. So the first thing that we need to look at here, if we look at the sine of that angle, can anybody figure out an expression for the sine of that angle using x, y, 1, and all that kind of stuff in the triangle? Yeah. Y. Brilliant. Yeah, it's not even 9 o'clock yet on Monday, and you're on fire. So how did you do that?
Because it's opposite over hypotenuse.
Yeah, opposite over hypotenuse, and in our case, that's y over 1. So the sine is just y. Okay, so when you are on the unit circle, the y-coordinate is the same as the sine of the angle. So that's what we're going to put in here. It's the sine of theta. Okay. How about the cosine of theta? Oh, how did you get that? Right, so it's x over 1. So we're dealing with x, and this is the cosine of theta. How about tangent of theta? Yeah, this is the opposite over the adjacent. So there's one more thing we could do here, which you may not have ever realized this, but y over x, from now what we've figured out, y and x have this other new connection, so I can call it the sine of theta over the cosine of theta. So that gives us some new information you might not have seen before about the tangent. Okay, so those are the connections in the unit circle that you must know. That if you're a point on the unit circle, the x-coordinate represents the cosine of that angle. If you are the y-coordinate, you represent the sine of the angle. We're going to practice using that in just a second here, but we also want to talk about the equation of a circle. So, how do you think you could describe a circle? Yeah, it's how would you explain? How could you draw a perfect circle? Anybody know? Compass? Yeah, what does a compass do? Draws a circle. I guess I walked into that one. But why does it make a perfect circle if you use a compass?
Because it has the same radius.
Same radius, fixed distance, right? It's a set of points around a fixed distance. So if we were to write down the distance on these points, x squared plus y squared equals 1. This looks like Pythagoras to you, right? These are the sides of a triangle. So x squared plus y squared equals 1. And I guess you'd put squared, but... So even though that looks like the Pythagorean theorem, it also describes what a circle looks like. It's funny because you don't have like a y equals. We could solve for for this equation for y and do some magic to it. But the way you're going to see it written in the form is like this. X squared plus y squared equals 1. Now, what do you think? What if we change the radius? What do you think would happen if, for example, I made it a radius 2? So it goes out to here now. You don't need to dirty up your notes like this, but let's just say I was there. Okay, this is still xy. What do you think the equation of this circle is? What do you think? The really big, terrible looking circle?
Is it the same?
Well, we're going to describe it with Pythagoras' theorem. We say the distance between the x and y has to add up to... So if we use Pythagoras' theorem to help us out again, x squared plus y squared equals 2 squared. So the equation would be x squared plus y squared equals 4. All right, last and most challenging one. What if we had a circle with radius r? Now we're getting there. X squared plus y squared equals r squared. Okay? Now the other nice thing about doing transformations is you know that one bit of knowledge. If I wanted to tell you, well, I don't want a circle that has center at 0, 0. I want you to move it to the left 1 and down 3. You should be able to transform this equation so that you end up with circle that's been moved as well. Okay? But for our purposes, we don't need to be super experts on it. We'll show you some of the things and the ways that we'll end up using it here. Okay, so first question is, are we on the unit circle? Because we could be on many different kinds of circles. How can you test if these points are on the unit circle? Great idea. Test the points to see if they fit in that equation, that the radius is 1. So here's, for example, the first one, if I went 1 over root 2 squared plus root 3 over 2 squared, that's 1/2 plus 3/4. So 2/4 plus 3/4 is close, but not on the unit circle. Because 5 over 4 is not 1. We were looking for 1. Right? Okay, you try the second one. Is the second point on the unit circle? All right, so what do you think? Is this point on the unit circle?
Yes.
Good. So we can double check it again. 1/2 squared plus root 3 over 2 squared. And I'm going to end up with 1/4 plus 3/4, 4/4, which is a 1. So yes, it's on the unit circle. So here's the way that you can interpret this picture. And again, I never make any claims at being a great artist, so bear with me. If I move over to 1/2 and up to root 3, here's that point. And here's the angle that I would make with that point. Tell me what you know about this angle here, just by using the values that I've got. No calculators, you look at it and you say, that's genius. If you know that's 60, yeah. But we haven't discussed that specifically in our class yet, so you probably learned that last year or at another place. So there's something you're supposed to know about this now. There are special triangles there, yes. We have not discussed that in our class, so don't worry if you don't know what they're talking about yet. But we just discussed a connection between the unit circle and points on the unit circle and angles and that kind of stuff. What do you think? Okay, keep going. What about x and y? We don't need to know what the number of the angle is, right? Don't worry about that. How do you make this connection? What is it? See if you can beat the projector up to it. Any ideas? We're gonna put this into that triangle we have. So one thing I know, and it is strange the first time you start working with it, is I know that 1/2 is the cosine of that angle. Why do I know that? X is the cosine of the angle, right? What else do I know about this angle? Okay, what about the sine? Okay. Does anybody know what's the tangent of this angle? Sine over cos, okay. So what is it? Yeah, √3. Nicely done. Okay. So be aware, there's going to be times when I say you may not use your calculator, and this is what I will expect you to know. You may not have the calculator with you. You will have to use the unit circle in order to determine, oh, I know what it is. Its sine is the y coordinate, and its cosine is the x coordinate. Or its tangent is sine over cosine. All right, so we're still going to keep playing on this unit circle. Okay. What are all the points where the x coordinate could be 1/2? Okay. So think about that. What points could it be where the x coordinate is 1/2? I'm going to pause and let you guys work on that for a minute. There's more than one. Okay, so there's a couple strategies that we could talk. The first one is if you know this is going to be on the unit circle, then this is another thing that we have at our disposal. So I can use the x coordinate in there and figure out what the y values should be. So one way I could do it is go 1/2 squared plus y squared is equal to 1. So 1/4 plus y squared is 1. So there's two other spots. The points would be at 1/2 √3/2, which we just saw above, and also at 1/2 and negative √3/2.
Do you have to simplify the whole way through, or can you just leave it at √3/2?
You should simplify it at least to this, right? It's not that much of a stretch, and it will help you when we start connecting them to the special triangles, which you see just underneath here, okay? Okay, the other way you can think about it is if you consider this on the unit circle, there's a triangle in there, so we can describe that triangle like this. It's on the unit circle, so I know that this has to have a length of 1, right? I know the x coordinate is 1/2. So I got to figure out what's the other side of the triangle. So you'd go 1 squared minus 1/2 squared, and I end up with the 3/4 that we had before. So this will be √3/4 or √3/2. So how could I draw those triangles? Here's where they would go on the unit circle. One of them could go like this, and the other one could go like this. Okay, both of those have 1/2 for the x coordinate, 1 for the radius, and this one is √3/2, and this one will be negative √3/2. So the important part to remember is it's not just one triangle. There's going to be another one because I can turn it upside down and still have the x-coordinate be a half. Okay. There is another way to connect them all up, but you need these special triangles we're going on to. So last one then, see if you can do this one. Either method that you like. If the y-coordinate is negative 1 over root 2 and the point is in quadrant 3, what point am I talking about? Okay, so I'm going to have to move some of this out of the way here just so we can discuss. So this is, get rid of this for now. It's always a good starting point to get some thoughts on the paper. So the thing I would do if you're not, you're still trying to get the hang of this, which I imagine is most of us, is to start with the unit circle and draw it, right? Or a unit dented circle. Now, what I'm going to do is I'm actually going to draw. It doesn't have to be perfect, right? I mean, you can guess that it's over here. You could guess that it's over here. That part's not a big deal. We're just going to put a point in quadrant 3. So if you've forgotten over the weekend, there's quadrant 3. I'm just going to put a point there. So this could be the angle I'm looking for that I've drawn. And now I'm going to put in the stuff that I know about this triangle in the unit circle. I know that it has a radius of 1 because it's the unit circle. And this is negative 1 over root 2. Does it make sense why it's negative when you look at that picture? Tell me why. It's going down, right? It's underneath. So what should you think about your answer for x right now? If you knew nothing else, you should be able to tell me one thing about what your answer is going to be. It's negative, yeah, because it's on the left side, right? So what we're trying to do is we're trying to figure out is what's this? Okay. So if you were to solve it using Pythagoras, right, you're going to say 1 squared minus negative 1 over root 2 squared. And you're going to go, oh yeah, that's 3/4. So root 3/4 is root 3 over 2. Sorry, getting excited here. That should be a half, right? So then you're going to go root 1/2 is 1 over root 2. And you lose a mark there when I go over your quiz. Because you go into autopilot in this and you think that makes sense to someone in grade 9 who's doing Pythagoras on triangles, but ours moves around the unit circle. The x-coordinate should be negative. Your answer should not be this one. It should be negative 1 over root 2 because it's over here in quadrant 3. It goes to the left. So this quantity is actually negative 1 over root 2. The x-coordinate's got to be negative in your final answer. Okay. That's why there should be a plus and minus when you solve. And that picture tells me which one I'm looking for. Right? If I know it's going to be on the left side, it's got to be a negative. I reject the positive one. The positive one is when, let's see here, I'd have, be somewhere on this side then. Oops, sorry. That would be my other possible triangle, because this is also negative 1 over root 2 for y and a 1. This would be the positive 1 over root 2. But that's not the triangle you're looking for, right? So it definitely helps to get a picture going when you start out. Okay. So as I mentioned, the unit circle connections are big. The next biggest connection we're going to be using is the special triangles. And they're probably the most common use in trig. So if you're finding values, unit circle is one way to find them without your calculator. The other way is with these special triangles. Now, I'm going to show you how you get them. Okay. The first triangle, what we do is we go 1, 1, root 2. So I remember this as the isosceles length 1. Okay. And what do you think these angles are going to be in here if I have an isosceles triangle? 45, yeah. And remember in our language, 45 degrees also means, yeah, pi over 4 radians. Okay, so that's the angle you're looking for if we're talking about radians. If we're talking about degrees, is 45. Okay. Now there's a problem with this, and the only problem is, if I was to look at it, okay, it's too big. It's not fitting on the unit circle, right? It's smaller than that. So how could I scale this so that it would be on the unit circle? Like the triangle is the same, but to fit it on the unit circle, right now its length is root 2, but I would like that to be 1. So how do you get it onto the unit circle? That's not the same triangle though. Not quite. Well, we're going to scale by root 2. Because if I divide everybody by root 2, okay, that's how you fit the triangle on the unit circle. Because now that triangle has radius 1, it'll be on the circle with radius 1, and each side is 1 over root 2. Okay. Now, in the second one, the special triangle, it starts out, we do an equilateral with length 2. Okay. And then we cut it in half. So the reason I'm going to these lengths to show you is because, honestly, you need to learn how to rebuild these. You don't want to memorize all these angles and values. You just want to know one of them starts as an isosceles length 1. The other one is equilateral length 2. So here's what I do. I cut it in half. If it's an equilateral triangle, what's the angle all the way around? Yeah, 60, 60, 60, and we chop it in half. So what do you think is going to happen to that angle there? Good. Okay. What do you think is going to be the length over here now that I've cut it in half? Okay. Can you figure out what's the missing side now? We only have one side left. Yeah, root 3. You can just do it by Pythagoras, right? So there's a special triangle. If you need to put it on the unit circle, so somebody's already read this, it's right there, we can scale it by 2. So for example, this now would have a length 2. If I stuck it on the unit circle, it wouldn't fit. So if I divided everybody by 2, now I'm on the unit circle. I'm going to be perfectly honest with you guys. If the question is asking for the unit circle, that's the only time I scale those triangles. I don't scale them unless I'm actually dealing with a unit circle. Otherwise, if the question does not force me to do that, that's just an extra work for me. So those scaling is not useful to you unless you're dealing with the unit circle specifically, okay? Which comes up enough, but... All right, so we should be able to answer some stuff now, like what are the coordinates for the given angles on a unit circle? So for pi over 3, okay, I'm going to draw the first one for you just so you can get the hang of this. It's not so scary, it's just unfamiliar territory. So which quadrant is pi over 3 in? So here's pi over 3. It's 60 degrees. What do you know about your x and y coordinate, even if you know nothing else? X and y will be positive, right? They're both positive in this quadrant. So if I'm on the unit circle now, okay, what are the coordinates here? Now the way you do that is you say, oh, that triangle looks familiar. Here's a triangle with 60 degrees. So what would be the point, oops, on the unit circle if I was at 60 degrees? I would be 1/2 over and root 3 over 2 up. Here's the 60 degrees. I go over 1/2 and up by root 3 over 2. Okay, so using your special triangles now, see if you can find the points for 7 pi over 6 and 3 pi over 2. Okay, so let's talk about these two. I know it's strange now. I'm telling you we're going to do this for the next 2 units and into calculus when we get there. So just bear with it. You're going to have to practice before it gets more familiar. 7 pi over 6. first of all, get a picture going. Here's our graph. 7 pi over 6, which quadrant's that in? 3. Okay. Remember, it doesn't have to be perfect where your angle's drawn. You just need to, try to make sense of what you're doing. So I know that has a length 1. If it was 7 pi over 6 to get here, what's my reference angle? Oh, sorry. Thank you. If you look at it upside down and backwards, it's in quadrant 3. There, that's quadrant 3. Yes, thank you. 7 pi over 6. Okay, so if that's 7 pi over 6, what's the reference angle that gets me inside the triangle? Yeah, 30 degrees, or this one in here, that's pi, and if this is 7 pi over 6, then between them would have to be pi over 6, right? So my reference angle here is pi over 6, or 30 degrees, if you're more comfortable. So we go to our special triangles then, and we say 30 degrees, where are you? Here is 30 degrees. And in this case, when I move over, I'm going to be, I guess I can draw it upside down to help you make sense of it. Okay, so here's 1, and then 30's up here now. So I know 60 degrees must be there. So root 3 over 2 is here, and 1/2 is there. So I just turn the triangle so that it matches up with this one in here. So that means my coordinates are down there. And the coordinates will be -1/2 and negative root 3 over 2, because I'm going left and down. Okay. Did I switch? Yeah, you're right. Yeah, it is too early for math. Negative root 3 over 2 and -1/2. Sorry about that. Okay, so coming at you later will be questions like, what's the sine of 7 pi over 6? The process is identical. What's the last step in telling me what's the sine of pi over 6 without your calculator? Of 7 pi over 6, sorry. -1/2, yeah, it's the y coordinate, right? So we're getting there. What about 3 pi over 2? What angle is that? Well, it's kind of like a 90. It's 270, right? It goes all the way to the bottom. So if we think about whoops, my apologies. If you think about 270, where is this, right? Start with your picture. That's 3 pi over 2 there. There's no triangle there, because I have to make an angle between this point and the x-axis. So when I do that, I end up with a flat line. So are we stuck? How would I figure out what's the coordinates here? Good, yeah, it's not as complicated as special triangles, right? If I'm here, the x-coordinate is 0 because I'm straight in the middle. And it's a unit circle, so the radius is 1. Stop it. So that means I've dropped 1 unit down here. Okay. So 0, -1, that's the coordinate if you're at 3 pi over 2. Okay, what's the cosine of 3 pi over 2? 0, yeah, the x-coordinate, okay? Okay, so now we're going to do the same thing backwards, okay? If I tell you the points, what's the angle that was formed? So we're still going to use a special triangle, we're still going to draw a picture, but we have to repiece the things together. So let me show you the first one just to make sure we're on the right track, because I know it can be a little strange to start with. Here's our unit circle, and I know I'm on -1/2 and then root 3 over 2, so it's going to be over here, something like this. Remember, it's not essential that it be perfect. So this will be negative 1/2. This will be root 3 over 2. This will be 1. So my job now is I got to look up my special triangles, right? What angles go in there for my special triangles? Yeah, it's actually lined up perfectly on your page. It looks exactly like that. This is 60 degrees. This is 30 degrees. So if I know that 60 degrees in there, what's the angle that was actually used? Yeah, 120. Because this would be 180 degrees here. Okay, so 120 degrees, is that my answer? It is, but it isn't. Why is it is and isn't at the same time? Yeah, the question here asks for radians. So be mindful of what you're asked to give your answer. This one says radians, so we'll make a conversion. That's going to be 2 pi over 3. Okay, so in radians, what's the angle that's made if I was sitting at this point on the unit circle? Okay, so there you can have a look and see how your answer compares to mine. I've been full of careless mistakes this morning, but hopefully that, does anybody else have that answer? Some people nodding heads? Okay, so I think I did okay. So label your points, right? Draw a picture. Which triangle is it? If you look at your special triangles, that's going to be this one over here. This triangle has the 45-degree angles in it. You might forget from, I can't even remember what grade we do this in anymore. It's honestly one of those skills which I only have one good reason for you why you need to learn this, and that's so that you can do limits in calculus. But if you were to rationalize those denominators, root 2 over 2 is the same as 1 over root 2. Okay. The other clue you have is the only triangle with root 2 in it is this one over here, right? So if I know which triangle I'm dealing with, it's 45 degrees in both corners. So if my reference was 45, it was 315 degrees all the way around, and 315 degrees is 7 pi over 4.